right, so in this video we are going to be talking about energy and reactions, otherwise known as thermodynamics. Now, thermodynamics may sound a little scary, but I promise you it is not bad at all. Okay, so the first thing we're going to do is define exactly what do we mean by energy. And while the true definition of energy is the capacity to do work, we're really going to focus on specifically energy and chemistry. There are going to be two types of energy, and this is true no matter what science you end up taking. So stored energy, for us, I want you to be thinking about this in terms of the energy that's stored in bonds, right? That's going to probably be the most useful stored energy, potential energy for us in terms of thinking about that stored energy. And then kinetic energy is energy of motion. And we've talked about a little bit about this before. To think about this is how it relates to temperature. Right? And so the faster something's moving, the more kinetic energy it has. And so as I increase the temperature, I increase the movement of those molecules. I make them move faster. And so those molecules at higher temperature are going to have a higher kinetic energy. The next thing to talk about in our discussion on energy is a thing called an energy diagram. A little bit later, we are going to ask you and have you identify all the different pieces of an energy diagram. First thing I want you to point out is we usually have energy, we always have energy on the y-axis. And then we have the reaction coordinate here. So the reaction coordinate is essentially the progression of the reaction. We always have our reactants at a given energy, and then we always have our products at a given energy. And we'll talk about how to interpret that difference between your starting energy and your final energy. We've talked a little bit about the activation energy, right? And that's the amount of energy you need to get that reaction going in the first place. Okay, so let's talk a little bit about that activation energy. This is the minimum amount of energy that's required for that reaction to take place, for it to move forward. And we've already touched on this, right? We've said that the lower the activation energy, the faster that reaction is going to go. The higher the activation energy, the slower that's going to go. And you want to think about how difficult it is to overcome. If you have a large activation energy like you do here, that's going to be much harder to overcome, and so therefore it's going to be a much slower reaction than if you have a small activation energy. And then keep in mind catalysts, right? We talked about catalysts already, and they are going to lower the activation energy. And if you can lower that activation energy, you can make that reaction go quicker. All right, so let's talk specifically about the energy that we experience with reactions. Now, most of the time when we are talking about energy and reactions, we are talking specifically about heat. We are going to define heat as this term right here. This is delta H. It is also called enthalpy, or the heat of the reaction. Now, reactions come in two flavors, right? Heat can either be released or heat can be absorbed. If heat is absorbed in a reaction, then that reaction is defined as being endothermic, and heat would end up being on the reactant side of the equation. If we tell you how much heat is involved for an endothermic reaction, we will give you that delta H value as a positive value. What that means is it doesn't mean that it's positive heat, it just means that that heat is being released and that heat is being absorbed, and that heat that reaction is endothermic. Now, if heat is released, it is an exothermic reaction, right? So heat is released, heat will be on the product side of the equation, and then we will tell you that delta H, if we give you that value, we will tell you that that delta H is negative. And again, it doesn't mean that it's negative heat. It's just that sign helps us to know whether or not it's exothermic or endothermic. So if it's positive, it's endothermic, and if it's negative, it's exothermic. Now we can also tell if a reaction is endothermic or exothermic by looking at the energy diagram. So here in this first picture, your reactants start off at a relatively low energy and your products end up at a higher energy. This is how you can tell you have an endothermic reaction. Okay, if I were to take the difference here, this would give me a positive delta H value. So it is endothermic. My reactants have, my products have a higher energy than my reactants. In an exothermic reaction, my reactants have a higher energy than my products. And again, if I were to take the difference here from my reactants to my products, my delta H value would be a negative value. So make sure you can keep these straight, endothermic versus exothermic, when you have a positive delta H, when you have a negative delta H, and what side of the reaction that should be written on. And again, remember that endothermic, it goes on the reactant side, and exothermic, it goes on the product side. Okay, so heat is a form of energy, and this is something that can be measured. And so we're going to be focusing on two units for measuring heat, and that's going to be calories, and the unit we're going to use there is CAL, or the symbol CAL, and joules is a capital J. Now, a calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. You may see, if you are an avid reader of food labels, you may notice the calories in your food, and those are actually in terms of kilocalories. And so that's going to be 1 kilocalorie is equal to 1,000 calories. And you may also see that the calories given to you have a capital C. If it's a lowercase c, that means it is just calories. If it's a capital C, it's actually a kilocalorie. We're also going to be talking about this in terms of joules. And just a reminder, 1 kilojoule is equal to 1,000 joules. And then this piece right here, if you wanted to go back and forth between calories and joules, this would be the conversion factor that you would need. So in a reaction, you have two things happening. In order for that reaction to happen, the bonds of your reactants have to be broken, and new bonds are being formed in your products. Bond strength is defined as the amount of energy required to break a bond. So the stronger the bond, the more energy is going to be required to break it. In order to break a bond, energy has to be put in. So that process of breaking a bond is actually endothermic, right? So in order for that reaction to take place, we have to put energy in to get those bonds to be broken. Now, bond formation actually releases energy, and so that process of forming new bonds is exothermic. It is going to release energy into the environment. So again, you've got these two processes going on at the same time. You have to put energy in to break those bonds. Once those bonds are broken, new bonds are being formed, and that process is releasing energy.